बना लेना तो बोल रहा हूँ यार, क्या बात करती है।
Hello, good evening. Am I audible? And if is the screen visible?
Yes.
Okay. So, good evening, everyone. Today we will start with the class now. I was waiting for a few more people to join, but I think not many people are going to join today. So, anyway, welcome to the NPTEL online course on water and wastewater treatment. Uh, I think the power is fluctuating here. Just a minute. Yeah. So, so currently we are in week 4 now. So today we'll be discussing the concepts and solving some of the problems related to the week 4 concepts. The videos have already been shared with you, I hope. And as you all know, the course instructor for this course is Dr. Bhanu Prakash from IIT Roorkee. And I am one of the teaching assistant. My name is Akash Saha, and I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. Okay, so let's see the contents of week 4. So just a minute. Is the slide not changing? Okay. Yeah, I hope the screen is visible now. There was some power fluctuation, so that's why it got disconnected. So anyway, let's see, have a quick overlook of the week 4 contents. So in week 4, we started discussing about the primary settling tank, where we learned about the various parameters and how to design a primary settling tank. And then we moved on to the discussion about the biological treatment. So what is the BOD and how to remove them. Okay, and similarly the case for nutrients. And then we learned in depth about the activated sludge process, which we generally use to remove the organics, okay, the dissolved organics from our system. And we saw how to do the material balance in the aeration basin. okay, and the different aspects of the oxygen transfer and what are the various types and the basic principles related to that. So we'll be solving the questions related to these concepts only for today, and then if time permits we will solve some subjective problems also. So let's start with the first question. It says that which of the following are attached type treatment systems? So we have activated sludge process, trickling filter, oxidation pond, and rotating biological filters. So please drop the answers in the chat box. Which of the following are attached type treatment systems? So generally, for as far as treatment systems are concerned, biological treatment systems are concerned, we have suspended type and attached type. Okay, so there are various examples for suspended types, like the activated sludge process is one of the example of such suspended type. So when we talk about attached type treatment system, basically we need some media for the biomass to grow. Okay, we have some media on which the biomass grows, and and those microorganisms only help in degrading the organics. Okay, so here the correct answer, as rightly pointed out by you, will be trickling filter and rotating biological filters. Okay, so since it's a kind of filter, so on this filter media, we grow these microorganisms, and once they are once they are active, they will be able to degrade the microorganisms. Okay, so an attached type of system refers to the wastewater treatment process where microorganisms responsible for breaking down the organic matter adhere to a solid surface like the plastic media or rocks within the treatment unit. Okay, so whereas in the suspended growth system, the microorganisms are freely floating in the water. So can someone tell me any other example of attached type of treatment system? Any other example of attached type of treatment system? Apart from trickling filter and rotating biological filters, any other example of attached type? No idea. Have you heard about MBBR? Have you heard about MBBR? What is the full form of MBBR? So MBBR is nothing but moving bed biofilm biofilm reactor. So MBBR is nothing but moving bed biofilm reactor. So it's a modified version of ASP. So in activated sludge process, we in the aeration tank we let the microorganisms to move freely inside the reactor, right? It is not growing on any media. But whereas in an MBBR, in the same aeration tank, we will put some media, like some plastic media, and on that the biofilm will grow and it will move freely. So it's a combination of an attached growth system with being in suspension. Okay, so it's a modified version of activated sludge process. Yeah, DWATS module can have both attached type or suspended type based on the use case. It doesn't mean that all DWATs will have suspended or attached growth. It can have a combination. DWATs is nothing but decentralized systems. Okay, so instead of treating all the wastewater in a centralized system, we do a decentralized we make a decentralized treatment system for a small community or for a small society, and then do the treatment. So it can have a combination of anything. Okay, it can be attached, it can be suspended, right? Yeah, so that is all about suspended and suspended growth. Okay. Now a small numerical. It says that a certain type of bacteria multiplies by dividing into two cells every 10 minutes. Okay, so it is getting doubled every 10 minutes. So if you start with 2 into 10 to the power 5 bacterial cells in a petri dish, how many cells will be there after 40 minutes? Okay, so the doubling time is around 10 minutes, okay, for the bacteria. And for the initial concentration, we have something around 2 into 10 to the power 5 bacterial cells. And it is asking how many cells will be there after 40 minutes. So please try it out. So even if you don't know the formula, it's a simple mathematical question. So with the help of basic mathematics, you can solve this. It's kind of an aptitude problem. A, okay, 3.2 into 10 to the power 5. Any other answer? So the current answer is option D. It's not A, it's option D. Anyone who got the answer? Yeah, N will be equal to 4. So let's solve this. Yes, yes. So it will be like that only. So let's solve this. So basically, for others, just make a note. So, so the formula generally that we use, so numbers at time t will be equal to the initial concentration into 2 to the power d by t. Okay, so here nt is the final number of cells after time t. N naught is the initial number of cells. Okay, initial number of cells. Then this t will be equal to my time in minutes. Okay, and d will be the doubling time. D will be the doubling time. So my nt will be equal to, what is n naught? N naught is 2 into 10 to the power 5 into 2 to the power t will be 40 by 10. As you said, n is equal to 4. So 40 by 10 is also equal to 4. So we will get 3.2 into 10 to the power 6. Okay, so every 10 minutes is doubling. So like that, 4 times it will double. So it will become 3.2. So 2 will become actually 32. Okay, so that is the answer. Right? Yeah. Another small numerical. A wastewater treatment plant has influent MLSs as 5,500 milligram per liter. After a settling period, the volume of sludge in the settling tank is measured to be 450 milliliter per liter of mixed liquor. So calculate the sludge volume index for the given mixed liquor in milliliter per gram. So I have to find out the sludge volume index. So I hope you know why we measure the sludge volume index. So based on the value of sludge volume index, we try to find out the settleability of the sludge. Okay, how good it is in settling characteristics. Okay, so based on the value of SVI, we try to find out. So what is SVI? So what is the answer here? So please take care of the unit. The unit they are asking is milliliter per gram. Anyone with the answer? So sludge volume index is the ratio of, so it's the ratio of the volume of sludge, okay, volume of sludge divided by the mass. Yeah, 81.8 is the correct answer. So for others, I will just write it down. So answer question number 3. So here the volume of sludge is equal to 450 milliliter and MLSS, okay, is equal to 5500, right? So what will be my SVI? SVI is just nothing but the ratio. So 450 it is liter per liter and this is milligram per liter. Okay. So 450 milliliter per liter divided by 5500 milligram per liter. So this will cancel. We will get something in milliliter per milligram. So this is 0.0818 milliliter per milligram, but we have to convert it to gram. So it will be 81.8 milliliter per gram. Okay. So very simple. So that's how you have to do this. Right? Let's move on to the next problem. In biological nutrient removal, what is the purpose of using anoxic zones in biological treatment system? Okay, why do we use an anoxic zone? To promote the growth of aerobic bacteria, to facilitate denitrification, to enhance phosphorus precipitation, or to optimize the ammonia oxidation. Okay, B. Yeah. So basically, we all know for denitrification, we don't need oxygen. Okay, oxygen is not the electron acceptor for any denitrification thing. Right. So we need some anoxic zone where nitrate can be used. Okay, so in anoxic, oxygen is not the electron acceptor. So that's why to facilitate the denitrification, we use the anoxic zones. So in anoxic conditions where dissolved oxygen is nearly absent but nitrate is present, facultative bacteria will use this nitrate as an alternative electron acceptor instead of oxygen. This reduces the nitrate to the nitrogen gas which is released harmlessly into the atmosphere. Okay, so from, so what we generally do, we have ammonia in our system. So first with the help of aerobic conditions, okay, and with the help of nitrifiers, we try to convert this ammonia to nitrite and then nitrate. Okay, so once everything is converted to nitrate, we will transfer it to the anoxic zone. So there we have the denitrifiers which use the nitrate as the electron acceptor rather than the oxygen. Okay, and once we use the nitrate as the electron acceptor, this nitrate will be reduced to nitrogen gas and it will be removed from the system into the atmosphere. So it's a harmless way. Next. Calculate the specific growth rate of microorganisms per hour in an activated sludge wastewater treatment system where the maximum specific growth rate is equal to 0.4 per hour, half saturation constant is equal to 12 milligram per liter and the substrate concentration is 6 milligram per liter. So you have to calculate the specific growth rate. All the other informations are given. So please try to answer. So what concept will be applied here? Which equation? Any idea?
It's like mu equals to mu max times to the S
Yeah.
divided by half saturation constant plus S.
So what is this called? This equation is known as I discussed in the last class.
Monods?
Mondo equation?
Yeah, monod
Ah,
equation.
yeah,
Yes.
yeah.
So yes. So tell me the answer. What will be the answer? Zero 0.13. Yes. C is the correct answer. Okay. So for others, I will just quickly write the equation so that you can follow. So mu is equal to mu max S by Ks plus S. Okay, so here mu max is given as 0.4 into 6 divided by Ks is half saturation constant is 12 plus S again 6. So it will be 0.13 per hour. So this curve, if you remember, this is the curve. Here we plot it mu versus S, and this is mu max. Okay, and somewhere half of mu max we will plot the half saturation constant Ks. Okay. Next, in a wastewater treatment plant utilizing facultative ponds, what is the unexpected challenge that might arise during the winter season in northern regions? Enhanced microbial activity, reduced treatment efficiency, increased pathogen removal, or improved settling of solids. So suppose we have a facultative pond in the northern region. So what would happen? What will be the challenge? So yeah, all all of you have answered it correctly. It will be the reduced treatment efficiency. And why so? Because in the northern regions in the winter season, the microbial activity will reduce. Okay, the metabolism or the bacterial metabolism will reduce due to the lower temperature in the winter season. Okay, so everything, the efficiency of the removal of BOD, organics, nitrification, denitrification, everything will be affected. So the overall treatment efficiency will reduce. Also, the colder water is more viscous. Okay, so if the viscosity will increase, the settling of the solids will also be affected. Okay, and similarly the sludge digestion. So everything will be affected. So we won't have improved settling, we won't have increased pathogen removal, neither we will have increased microbial activity. So option B is the correct answer. Okay. Moving forward, a completely mixed flow reactor is designed with the following data. Q naught is equal to 20,000 meter cube per day. BOD after PST, that is the primary sedimentation tank, is 180 milligram per liter. BOD of the effluent is 10 milligram per liter. Y, that is the yield coefficient, is 0.5 kg per kg. KD, that is the decay constant, is 0.05 per day. MLSS or mixed liquor suspended solid is 4000 milligram per liter, and the underflow concentration, that is XU, is 10,000 milligram per liter for secondary sedimentation tank, and the mean residence time, okay, is 8 days. So what would be the reactor volume? So all the parameters are given here. So you have to find out the reactor volume. There is one equation. So just apply that equation and you will get the reactor volume. So I hope you are familiar with the terms of the activated sludge process, because these terms again and again we will use, okay, everywhere in every calculation. So you have to be very specific and you should know these terms, because everywhere the explanation will not be given, only maybe the variable name will be directly provided, like y, kd, xu, xr. Okay, so you have to be well informed about these things. Or if you want, shall I give a quick overview of the ASP and all the terms with the mass balances? If you want, I can do it right now. And maybe I can write down the major equations also, so that there will be a revision. Okay. So is anyone solving this problem? Or else we will just quickly see the concepts of this ASP. Okay, like how it is derived and what are the major uh, variables or constants that we have to focus. Okay, so let's keep this question aside for some time. I will come back to this again. Okay, so let's talk about ASP. So in activated sludge process, what we generally, so we have a primary sedimentation tank. Okay, so after the removal of the suspended solids in the primary sedimentation tank, what happens? This flow moves to an aeration tank. So this is an aeration tank. Okay, and here it is complete, it is getting mixed. Okay, so this aeration tank is there, and suppose the volume of this aeration tank is, volume is V. The volume is V. From this aeration tank, the flow goes into a sedimentation tank. Okay, from this aeration tank, it goes into a sedimentation tank, or we will call it as secondary sedimentation tank. Secondary sedimentation tank. Okay, this one, earlier one was the primary, here the secondary. So here generally the sludge will get accumulated. Sludge will get accumulated, it will be settled down. Okay, so from this, some part will be overflowing, okay, as the effluent, some part will be overflowing, and some, and this sludge will be rejected. This sludge will be rejected out. So rejected, and some part of this sludge will again be recycled into the aeration tank. Okay, is this clear? So can someone tell me why this recycling is required? Why this recycling of sludge is required?
For the growth of microbial
Yes, so
bacteria.
actually what is happening, uh, in this sludge, okay, with the organics, some much of the microorganisms are also getting settled, okay, and then it is getting rejected. But in the aeration tank, we want to maintain a concentration of microorganisms, okay, and we want it to be active. So that's why some part of the microorganisms are getting recycled again into the aeration tank. Yes, not to increase, I would say, but to maintain the microbial concentration and the activity. Okay, we have to maintain it. Okay, so now let's come to the notations. So always remember, we first have to, with three notations we generally use for any this kind of system. First is the discharge, how much flow it is coming, we denote it by Q. Then the biomass concentration, or the microbial concentration, we denote it by X. And then the substrate concentration. So substrate means what is the food or what is the BOD, because we use the organics as the food for the microorganisms. So substrate, okay, or the food, so we denote it by S. So suppose from the primary sedimentation tank, some Q0 flow is coming. Okay, some Q0 flow is coming with some very minimal microbial concentration of X0. So X naught, we generally take it as 0. We don't assume that any microbial concentration is coming, but still let it be very low, it be X naught. And the substrate or the BOD, like whatever BOD we want to remove, let it be S naught. Okay, let it be S naught. So this is the initial thing that is coming into the aeration tank from the PSD, from the primary sedimentation tank. Now in the aeration tank, okay, what will happen? This X naught will increase or decrease? What will happen? This X naught or the biomass concentration, bacterial concentration, will it increase or decrease? Any idea?
Maybe it will increase because we're supplying oxygen to it. Kind of we're
Yes.
activating.
Yeah, we are activating it, we are providing food in the tank, so definitely this biomass concentration will increase. Okay, it will increase, suppose to some value X. It will increase to suppose some value X. And what about S naught? Will it increase or decrease? S naught is the substrate or the BOD. Will it increase or decrease in the
Decrease.
reactor? Sorry?
It might decrease.
It will be decreasing. So, okay, it will be decreasing. Suppose it is decreasing to S. Okay, now one more question I would ask, like in the first or the second class, we discussed about various type of reactors, right? Batch reactor, CSTR, PFR. So what do you think this aeration tank is a type of reactor? What type of reactor is the aeration tank?
CSTR.
Yes,
CSDR.
it's a CSTR. So one important assumption that we made in CSTR is, suppose some influent concentration is coming, X, Y, Z, whatever. Okay, it is getting changed in the CSTR. So what will be my effluent concentration?
It will be the same as it is in the tank.
Yes, exactly. So it will be the same as the tank. So both this S or X will come out as it is from the tank. Okay, and what will be the flow that will be coming out of the tank? What will be the flow? So Q naught is coming in. So what will be the flow coming out of the tank?
Same.
Same. Okay, for now, let us keep it as Q naught only. Let us keep it as Q naught. But there will be some increase. Why there will be increase, I will tell you. Okay, let it be Q naught. Because as Q naught is coming, the same will be going out. That is true. Fine. Now, let's suppose from the secondary sedimentation tank, now it is going. So now some settling will happen, right? Some settling will happen. This biomass will be settling in the tank. So if the biomass is settling, what do you think will happen to the concentration? Will it increase or decrease with time? Well, whether it will be, my simple question is whether it will be more than X or lesser than X.
Because it's settling, it might be decreased.
No, it won't be decreasing. See, we have some concentration coming into the system, and over a period of time, it is settling and settling. So with time, the whatever will be accumulated inside in the bottom of the tank will be much higher than the concentration that is coming. Okay, much higher. So suppose this concentration is around XR, that whatever is settling inside. Okay, and the same thing will be rejected. So whatever is coming out from this tank will be XR. Okay, that is rejected biomass volume, and this will be much higher than the X, because over time it is settling. Okay, so this XR will be very high than X. Okay, and there will be no change in the substrate. Okay, because substrate there is no settling, nothing like that, because it's in dissolved form. So it will be staying as it is. It will be staying as S only. Okay, and I said that inside the secondary sedimentation tank, some Q naught value is coming in. Okay, so from that Q naught value, some QW value only I am wasting. Okay, I don't know what is this QW value, but some QW value is only getting wasted from the settling tank, right? So now you can see this Q naught is coming, okay, QW is getting wasted, okay. So what will be coming out of here? So how much will be coming out from here? How much of discharge will be coming out from here?
Q naught minus
So
QW.
Q naught minus QW will be coming out from here. Okay. Now all this time and there will be no change in S, because for S there is nothing is happening. No one is taking up that substrate value. Okay, and all the degradation has already happened in the aeration tank. For the BOD, all the degradation has happened in the aeration tank. So that's why that same S will be flowing throughout. So S will not change. Now coming to X value, that is the biomass value, this will be something around some XE. Okay, let's say some effluent biomass. So this also we will treat it as very negligible. Not much biomass is coming out from the system. All the biomass we try to concentrate inside the tank itself. So we have XR and XE from these 2 points. Now, okay, so now from this QW, okay, from this QW, whatever is wasted, let's suppose we are diverting some of the discharge, that is QR, to the aeration tank again. Okay, some of the flow, that is QR, is getting diverted. Okay, so S will again remain as such, and the uh, biomass concentration will be also same as XR. So this is again going into the tank. Okay, so now you can see that at this juncture, at this point, there are two flows coming. Okay, one is the Q naught, and one is the QR. Right, one is the Q naught and one is the QR. So that's why the flow that is coming out from the aeration tank will be Q naught plus QR. That's why I was not writing it earlier. Is it fine? Are you able to understand? Like why
Yep.
we added keyword? So this is the overall flow diagram, okay, with all the parameters, how it is changing, okay, whether it will be higher or lower or whatever, how it is varying, how it is getting degraded. So this is the overall picture of the uh, activated sludge process. Now we know there are several equations of this activated related to this activated sludge process. So those equations are nothing but the derivation of mass balance. Okay, I told you, like, we have to do the mass balancing. Okay, so sometimes we will do the mass balance for the biomass, sometimes we will do the mass balance of the substrate, and based on those equations only we are deriving those formulas. Okay, I will show you how we are doing it. So let's suppose, I hope you are fine with it. So now let's go to the mass balance. So let me do the biomass mass balance first. So I hope this diagram is clear to all of you, right? If you have any queries, just look into this once more. You can ask me right now itself, or you can later mail me, and if you have any queries. Okay. I hope this is clear, all the notations and all. Okay. Because these notations will be used again and again. Okay, so let's see the biomass balance, mass balance. So in biomass balance, what is happening? So let's see the aeration tank only. In and around the aeration tank, what is happening? Okay, in and around aeration tank, what is happening? So in the aeration tank, there is some influent biomass coming. Okay, influent biomass is coming. Plus some biomass is getting produced inside the tank, right? Okay, this will be equal to the effluent biomass plus some biomass that is wasted biomass. Right? Is it clear? Okay, so let's suppose in and around the aeration tank, some influent biomass is coming, some biomass is getting produced inside the tank. That will be equal to the effluent biomass plus some wasted biomass. Okay, So now if I want to do mass balance, what did I tell you? We have to multiply generally the discharge into the concentration, right? Discharge into the concentration. So what we will do? So influent biomass will be, what will be my influent biomass? Can someone tell me? Just see this figure and tell me what will be the formula for influent biomass. Any idea? I said that we are keeping the mass balance, so per unit mass will be constant. Okay, so if I want to do the influent mass balance, influent biomass, what will be the formula?
Q into X naught.
Yes, so it will be Q naught into X naught, not Q into X naught, it will be Q naught into X naught, right? So Q naught into X naught is my influent biomass that is coming. Now with time some biomass will be produced. Okay, so this we will denote it as V into dx by dt. Okay, so V is the volume. Okay, volume will be in meter cube. Now dx by dt will be milligram per meter cube, and by dt will be 1 by s. So this milligram millibar cancel, again we will get milligram per s. Okay, so mass per unit time again we will get. So that's why I denoted by V into dx by dt, because V is the volume of our tank. Now what will be the effluent biomass? Now tell me what will be the effluent biomass? This is the effluent.
Q naught minus QW into
Yes.
XE.
Yeah, nice. So it will be Q naught minus QW into XC, and similarly the wasted biomass will be nothing but QW into XR. Is it clear? Is it fine? So this is our biomass mass balance. And all this we are doing at steady state. So by steady state, I mean that with time, the concentration is not changing. Okay, so with time, the concentration is not changing. So it's very important to mention the steady state. Now next, we will do substrate mass balance. So in substrate mass balance, uh, so here also again, influent substrate. Okay, now here substrate won't be produced, but rather it will be, what will happen to the substrate in the aeration tank?
Decrease.
It will be
It will be
consumed or decreased. Yeah, it will be consumed or decreased. So I can write influent substrate. I will write it down, no problem. So influent substrate, okay, plus substrate consumption, substrate consumed will be equal to effluent substrate, okay, plus wasted substrate. Okay, so again here influent substrate will be Q naught into S naught, okay, plus, so now the substrate is getting consumed. So what will happen? I will put a minus sign and I will write V ds by dt. So substrate is getting consumed, okay, with time. So ds by dt is the change in substrates with time into the volume. So substrate consumed will be minus V into ds by dt will be equal to again Q naught minus QW into S plus QW into S. Okay, so this is the mass balance for substrate. Now, here we know all the parameters. Basically, we know mostly all the parameters, but these two parameters are somewhat unknown. I don't know how fast my microbe is getting produced or how fast my substrate is getting utilized. Okay, so these two things I don't know actually. Okay, dx by dt and ds by dt I don't know, so I have to find out this separately. So how do we find out this? So this is nothing but the biomass. First we will see what is the biomass growth or dx by dt. So this dx by dt, how we will write? We will write it as mu x minus k dx. So what does that mean? Mu x minus k dx. So mu, we know it is the specific growth rate. Okay, specific growth rate. Okay, and what is the kd? Kd is the decay rate. So when the biomass grows inside any reactor, okay, it grows following the Monod's equation, right? We have talked much about it. It will grow with respect to the Monod equation. So there is a specific growth rate, that is mu. So mu into x will give how much biomass is getting produced in a period of time, and kdx will be those things which will be getting decayed or which will be dying. Okay. Do you know the biomass growth curve? Anyone has any idea how does the biomass growth curve looks? Any idea? Have you heard about the log phase, lag phase, stationary phase, and then decay phase, death phase? So
Yes.
biomass growth looks something like this. Suppose it is with respect to x and t. So with time, at first there will be some small acclimatization. Okay, the biomass will try to settle in, it will try to adapt in the environment. So that time the growth will be very less. Okay, this is the lag phase. Then there will be a log phase. The biomass will be increasingly very highly, it will be increasing at a very fast growth. Okay, so that will be my log phase. Then there will be a stationary phase where there will be some increase as well as some decay. Okay, so effectively there will be not any increase in biomass growth. Okay, so that is the stationary phase, and the last will be the death phase. Okay, then the biomass will be dying more and more, and it will feed onto itself. So first is the lag phase, then we have the log phase, then we have the stationary phase, and then we have the death phase or the decay phase. So there will be some decay of biomass also. So that's why we will put in this decay constant into x. Okay, I hope this is clear. So that's how we denote the biomass growth, that is mu x minus k dx. So now what will happen? So this dx by dt will be equal to mu, we know mu from the Monod equation, it will be mu max s by ks plus s into x minus k dx. Okay, so this represents the growth and this represents the endogenous phase or the death phase. Right? I hope this is clear to all of you. Okay. Now the last thing. The is substrate utilization. So what is substrate utilization? I said that the substrate will be getting consumed, right? It will be getting consumed, it will be getting utilized. So now how to get that? Or we will say ds by dt. How to get ds by dt? So ds by dt we show it by with a negative sign because it is getting consumed, so negative sign. This will be equal to 1 by y into dx by dt. 1 by y into dx by dt. So here y is called as the yield coefficient. Okay, yield coefficient. So y is nothing but, if you see this formula, y is nothing but it's the ratio of dx by dt divided by ds by dt, right? So that means biomass growth rate, okay, growth rate divided by substrate utilization rate. Substrate utilization rate. So what does that mean physically or practically? What does that mean? It means that how much biomass is getting produced per unit of substrate given. Suppose I give 1 gram of glucose or 1 gram of BOD to my system. Okay, so in 1 gram of glucose provision, the biomass that is getting generated is 2 gram. Okay, so my yield coefficient will be 2 by 1, that is 2. So that's what means by yield coefficient. So how much biomass is getting generated with respect to my substrate given in the system per unit time, because this dt will anyway will get cancelled. So how much growth per unit of ds or substrate. Am I clear to all of you? Okay, so this is how we generally denote all these things. And now so what generally again some assumptions, some mass balance assumption is that we say that some assumptions, I will say, we will say that x naught that is coming into the aeration tank and xc that is getting removed from the secondary system is almost equal to 0. Okay, is almost equal to 0. So this is one of the assumption. And so all this equation, if you just uh, do some balancing here and there, you will get all the equations. So one of the equation is like for the volume. Okay, volume is nothing but q into theta cy into s naught minus s by x into 1 plus kd theta c. So here theta c is nothing but we call something as MCRT, mean cell residence time, or BSRT. Okay, biological resident time. Okay, so this theta c is nothing but Vx by QWXR plus Q naught minus QWXC. Okay, so this BSRT or mean cell resident means how much time the biomass is staying in the system. Okay, mean cell residence time. How much time the biomass is there in the system, we denote it by theta c. You might have heard something about HRT, that is the hydraulic retention time. Hydraulic retention time. But this is the mean cell residence time. So HRT or hydraulic residence time, we denote it for the how much time the fluid or the water is staying inside the reactor. This is for the biomass. Okay, so like this another equation is there. And apart from that, we can also calculate the s, that is again ks 1 plus theta c kd theta c by theta c yk minus kd minus 1. Okay, so all these equations are just derived from the parameters whatever we have seen here. I'm not going into the derivation; those derivations are not required. But if you, but you can see, you know v, what is x, qw, xr, x q naught, qw, xc, everything you know, right? So you can calculate theta c from here. And once you know theta c, we will put it in this equation and we can calculate what is the v. So like that, like so many parameters are there. Okay, one will be unknown, other will be provided to you, you have to calculate the missing one. So like that questions will come. Okay, any doubt regarding all these things? Any doubt which you are not familiar or aware? Anything you want me to clarify again? Just see this. Any doubt here? Because this is the main schematic. If you can understand this schematic, then the problem solving becomes easier. The derivations will be much easier for you to understand. Shall I move ahead? I hope this is clear.
Sir,
Yeah.
um, in the videos there was like monad equation, like limiting cases. The food is limited, like S if S is much greater than KS or S
Yes.
is much lesser than the KS. It was a little tricky for me. Can you explain this?
Okay, so they are asking the limiting cases, right? Okay, so basically what was happening, I'm not sure like what exactly they were trying to like comprehend from that. So we have mu is equal to mu max S by Ks plus S. So what was the first, do you remember what was the first case?
Yeah, it was like if the S is much greater than the Ks, then the equation for biomass increases, becomes zero order in substrate.
Okay,
And
yeah.
it all,
Suppose just imagine this S. Okay, this S is very much greater than Ks. Suppose I put Ks as 0.1. Okay, and this is something around 100 or 1000. Just think like that. Okay, that means whatever the half saturation substrate is there, from that our provided substrate is very high. So what will happen in this equation? The top half will remain as such S, or I can write it as 1000. So mu max into 1000 divided by something 1000 plus 0.1. Okay, which is almost equal to 1000, right? Almost equal. So this thing will cancel out. This thing will cancel out, and what we will get? We will get mu is equal to mu max. So that means he wanted to say so that if you see this graph, it is something like this. Okay, this is with respect to S and mu, right? If S is very high than Ks, suppose your Ks lies somewhere here, and we are taking some S value very far away from here. So what it means? It means that our S value has already received, our mu value has already achieved the maximum value. Okay, so that is why my mu becomes equal to mu max. Are you able to understand what I am trying to say?
yeah, it makes sense.
Okay, so here it means that S is very high than Ks. So whatever substrate you have provided, it is very high than the half saturation constant. So it means that the mu that will be there at that point will be achieving the maximum value. It will be achieving the mu max. So that's what it means. Okay. But if it is somewhat closer than the Ks or S value, then you have to solve it and get the value. Okay, it won't, it will be somewhere in this region, right? So like that you can do. Another thing, another important aspect in these thing is like we called something called as volumetric or organic loading. Okay, so it means that how much of BOD or in kg BOD we are supplying in the reactor or in the volume per day. Okay, so we have a tank. So you should know that the microbial concentration will have a capacity, right? It won't be able to treat too much of organics, right, for a given period of time. So we have to maintain some organic loading that is coming into the system. So that's why this volumetric organic loading is very important to maintain inside the reactor. So we should know how to find this out. So this volumetric loading rate is nothing but the discharge into the BOD or S value, whatever is, by V. Okay, or I can write QS by V. So this is the volumetric organic loading. Another thing is the food to microorganism ratio. Food to microorganism ratio. So this is also you have to maintain, because per unit of microorganism, how much food should be provided, how much substrate should be provided, should also be taken care. Okay, so this is we find out by QS by V into X. So just a small difference, only V into X will come instead of by V only. So F by M is equal to QS by V into X. Okay, or instead this is not QS, we should write it as Q naught S naught by V into X, because Q naught S naught is the food that is coming inside the reactor. So Q naught S naught by Vx. So like that you have to solve. Okay, so these are some of the things that you should know. Now let's come back to the problem. So here, see, so many parameters are given. Q naught, okay, BOD of effluent, uh, so Y, KD, everything is given. So now you have to find out what is the reactor volume. So can you solve it now? I'll wait for some time. 2428.57. Yes, exactly. That is right. That is right. So how did we get this? How did we get this? So I think, yeah, this equation is already there. Okay, this equation we have to apply. This equation. So I will just write it down here. So this is question number 7. So V will be equal to Q naught Y into theta C into S naught minus S divided by X into 1 plus KD theta C. So here Q naught value is nothing but 20,000 meter cube per day. What is Y? Y is 0.5. Theta C is equal to 8 days. Okay, 8 days. Then what else? KD is equal to 0.05. And S naught initial is 180. S is 10. So once you put all these value in this, and X value is also given, X is 4000. That is the biomass concentration. So from the given information, you should know what are each of these parameters. Okay, it will be given in words. You have to find out what does each of these things indicate, because here in the question they have not written substrate. They have not given what is S or S not or S. They have written what is the BOD. So you should know that BOD itself is called as the substrate. Sometimes they will say some glucose is added. So glucose will be the substrate. They will say the microbial concentration is this much. So microbial concentration means the biomass, that is X. So you should know all these things. Milligram per liter. Okay.
Sir, how about the units? Shall we keep it like for the X as milligrams per liter, or we should change it?
Sorry, for what? I didn't get your point.
Yeah, I was telling that. Shall we keep the units as it is in the question, like in milligrams per liter for the X, or we should change it to like kilograms per cubic meter or something?
No, so generally in this equation, it will state as milligram per liter. You don't have to convert anything. Okay, because ultimately if you see in the numerator you have S, so it will be in milligram per liter, and in the denominator you have X, that will be also in milligram per liter, so both will cancel out with each other. Okay, so if you are taking biomass in milligram per meter cube or something, then you have to take the substrate also in milligram per meter cube. Okay, because this thing and this thing both have the same uh, it should have the same unit, then only they will cancel out. Okay, so actually ideally in these questions the only the this time factor, this 8 days or how many months or how many weeks, this only sometimes have to be taken care. Other things that will take care of itself, so you don't have to worry much about it. Okay, it will be in the standard units only. Okay, right. So that's how you have to do. Let's move to the next problem now. Okay. Now the next problem says that heterotrophs are organisms that cannot produce organic compounds from inorganic sources, and therefore they rely on obtaining preformed organic molecules from external sources. Then statement B, autotrophs are organisms capable of synthesizing organic molecules from simple inorganic substances like carbon dioxide. So what do you think is true or false? So we are comparing heterotrophs and autotrophs. I hope you are aware of these terms. These terms. No idea about this? You can make a guess.
C.
C. Yes. C is the correct answer because both of the statements are true. Uh, because the heterotrophs, they have to depend on external sources for of organic carbon, okay, for their energy and growth, and autotrophs can produce their own organic molecules with the help of inorganic substances like CO2. Okay, so one is based on external organic sources and another is based on inorganic sources, which so that they can make their own organic molecules. Okay, so it is true. Okay, this is an question. We will come back to this because this looks a very big problem. I will show you a simpler version of this first and then we will solve. So let's leave this for now. Grit and sand particles are usually removed from wastewater by which type of settling? So this is very easy. So we have talked much about it. So B, yes. So discrete particle. This is very easy. We have discussed these things in detail. So let's move. Alright. Find the terminal velocity. I think this also we have solved enough times. Terminal velocity using the Stokes law. So I am skipping this question for now. Yeah, this question is somewhat interesting. So we have a water sample that has particle distribution as shown below. So we have a size of 0.3 and zero point 0.4. Okay, two different sizes are there. The quantity of zero point 0.3 size is 40%. The quantity of zero point 0.4 size is 60%. Now the settling velocity is also given. For zero point 0.3 it is 0.25 and for zero point 0.4 it's 0.3. Okay, so now the total solids in suspended form is 500 grams. So the total sample of the water is having the solids as 500 grams and the design overflow rate is 0.3 mm per second. 0.3 mm per second. So you have to find out what will be the efficiency of the horizontal flow sedimentation tank with respect to the mass removal. Okay, so we have solved problems like this, but it's a combination because there are two different sizes are given. Okay, we have solved some problem where only one size was given. So here two different sizes are given. So you have to find out what is the percentage removal when two different sizes are given, because they both will have different settling velocity, right? Because the size is different. So you have to find out what will be the efficiency. So any idea, any basic idea or concept that you can tell me to solve this problem? You don't have to solve it, but anything that you want to say, like how we will approach this kind of problem. So what is the first thing you will notice here? So we have the settling velocity is given and then the design overflow also is given. So what we can say about the particles now? Just see, the units are same. It is mm per second. So don't need to worry about the unit. So what you can say about these particles? Two types of particles are given. Yes.
If the settling velocity is 0.3 and the size is 0.4, it's like 100% removal
Yes, exactly.
because
Yes. Yes. So any particle of zero point 0.4 or more than that. Okay, so any particle of zero point 0.4 size or more than that, it will be removed 100% because their settling velocity is zero point 0.3 or more. Okay, and what about 0.3 size particle? How to find out the ratio or how to find out, sorry, the removal efficiency? What will be the removal efficiency? Any idea? Okay, so one thing you have told correctly that, so let's solve this problem. So what is happening is, so we would say that the settling velocity of 0.4 mm or greater size is greater than or equal to 0.3 mm per second, that is the overflow rate. Okay, that is the overflow rate. So all these solids will be removed 100%. Okay, 100% it will be removed. So what is the weight of 0.4 mm size particle? It is given as 60%, right? 60%. So 60 by 100 into what is the total weight? It is 500 grams. So 60 by 100 into 500. So 300 grams will be removed 100%. Totally, it will be removed. Now what about the rest 40%? Okay, so rest 40% is there. So now we know that the settling velocity of 0.3 mm size, the settling velocity is around 0.25 mm per second. So this will not be removed 100%, it will be somewhat lower than this. So how to get that? So efficiency will be, so efficiency of those particles will be equal to 0.25 by 0.3. Okay, it will be just the ratio of their settling velocity with the overflow rate. Okay, nothing but 0.25 into 3. So what will be now weight of 0.3 mm size particles that will be removed? So it will be equal to the efficiency into weight into the total weight. Okay, into the total weight. So efficiency is 0.25 by 0.3 into 40% of 500. Is it clear? 40% of 500. So this is around 166.67 grams. So what is the total removal? So total removal is nothing but the first 300 grams and then 167.67. So it will be 300 plus 166.67, that is 466.67 grams. So what is my total efficiency? Total efficiency of particle removal So we had around 500 grams. So out of that 466.67 is getting removed. So 466.67 divided by 500 into 100. So that is 93.33%. So my removal efficiency is 93.33%. So that's how you have to do it. Any doubt in this? Okay, so 4.4 mm size, since the settling velocity is equal to the overflow rate, so 100% will be removed. Okay, so 100% will be removed means, so whatever is the weight of 0.4 size particles, everything will be removed. So we have 60% of those particles. So 60 by 100 into 500, we got 300 grams. Now for the 0.3 mm particle, we know the settling velocity is 0.25. So the removal efficiency of 0.3 mm particle will be 0.25 by the overflow rate. So 0.25 by 0.3. So now how much 0.3 particle size is there? That is 40% of 500. So we'll multiply the efficiency with the amount of 0.3 particles. We get 166. We will add both the amounts. We will get 466. Then the total removal efficiency will be 466 by 500. Am I clear? Any doubt in this? Is it making sense? Okay. If you have any issue, please let me know. So this is how you have to do it. Now next. Okay, so now these kind of problems will come. They will tell you an aeration tank with all, so MLVSS is nothing but the X. Okay, so mixed liquor volatile suspended solid is X value of 3000 milligram per liter. The plant received the effluent BOD of 208 milligram per liter. Okay, primary effluent. So that means the BOD value or substrate value is given. Flow rate Q naught is given 12 mld. The aeration volume is 1875 cubic meters. So V is also given. You have to find out the F by M ratio. Okay, as I told you, it is nothing but Q naught into S naught by V into X. So if you solve this, so F by M is equal to Q naught into S naught by V into X. So if you just put the values, you will get 0.444. So these are just, so most of the problems here in this chapter will be like this. Okay, you will be given a set of values, you have to then calculate it. I'll go to the next. Wastewater has various kinds of nutrients present which can be used by microbes for cell synthesis. Select the nutrients which are categorized as major nutrients. So which of them is the major nutrient? Tell me.
Calcium.
So here we are talking about the cells synthesis. So with respect to that, the major nutrient that we generally call them as phosphorus and nitrogen. Okay. So other things we are the minor nutrients. We don't focus much on them. We mostly focus on the nitrogen and phosphorus. Next, which of the following is not a step in the activated sludge process? Okay, so we have learned in detail about the activated sludge process. So which of them is not a step? Mixing and aeration, settling of mixed liquors, suspended solids to separate the sludge, anoxic condition for denitrification, drying of sludge, or flocculation of the mixed liquor.
A. Mixed and aeration of mixed liquor.
Okay, so let's go back to the thing again. So here actually, see, mixing and aeration will happen, that we know. In the volume, in the aeration tank, the mixing and aeration will happen. Settling of mixed liquor, this will happen in the secondary sedimentation tank. Okay, there the settlement of the biomass will happen. So that's why settling will happen. Now coming to anoxic condition for denitrification. So this also happens in a ASP. We provide a separate zone for that. Okay, so we add some more compartments with the ASP for the denitrification to happen. Okay, so though in our calculations we have not shown the denitrification part, but in reality there are some selector zones or some additional units that are added with the after the aeration chamber for the denitrification to happen. Then flocculation of mixed liquor, obviously the flocculation will happen, then only it will be settling faster. So flocculation can also happen. The drying of sludge, this doesn't happen. This is a part of the sludge treatment facility. Okay, so once we extract the sludge, whatever is wasted from the secondary sedimentation tank, that is then being processed. So there we go for drying. So drying of sludge is not the part of the ASP, right? So this is again the schematic of that. So drying of sludge is not the part. Okay. The composition of total Geldal nitrogen in domestic sewage is expressed in milligram per liter as nitrogen, which is the result of the addition of. So we call something as total Geldal nitrogen. So what is this addition of? Organic and inorganic sources, nitrogen from organic and nitrite, nitrogen from organic and ammonia, or ammonia and nitrite. So the correct answer for this total Geldal nitrogen is the nitrogen sources from the not inorganic, from the organic sources and ammonia. Okay, and ammonia. So if you remember in the first class, we told that if ammonia is present, it's a recent pollution, right? So ammonia tells something about the recent pollution uh, of the river or something. So that is why most of the nitrogen present in the river or in anywhere in any system will be in the form of either organic nitrogen or ammonia. Okay, then it gets converted into nitrite, nitrate, or nitrogen gas, whatever. But in the start, it will be in the form of organic sources and ammonia. So that's why to quantify this, we have devised a term called as total geldal nitrogen, okay, of the domestic sewage. Okay, so it is option C, organic sources and ammonia. So yeah, this is again another problem. Flow, BOD, everything is given, and you have to find out the MLSS. MLSS is nothing but X. So we will not waste much time in this. So this direct formula we can use. Okay, so if you put this all the parameters in this formula, you will get the value of X. Right? Okay, yeah. Now this formula, this question we can solve. So consider a wastewater plant which is set up in Shimla. So the elevation of the city is 258 meter. Annual average design temperature is 20 degrees Celsius. So this question basically talks about the oxygen transfer rate. Okay, so many places we provide the aerators to provide the oxygen. uh, we have the aeration tank where we provide the oxygen, but when we provide the oxygen at any particular system, the amount of oxygen that is transferred from the system depends on various factors. Okay, depends on various factors like what is the elevation of that place, what is the saturation oxygen level, okay, what is the pressure at that place, what is the atmospheric pressure, okay, what is the oxygen transfer ratio. So all these parameters affect the transfer of oxygen rate, okay, in an oxygen tank. So that's why this question is there. So you don't have to worry much about it. Just again, you have to memorize the formula here. Okay. So first we will calculate what is the concentration. Okay, what is the concentration of average oxygen in that? So that is equal to the standard concentration into 0.5 divided by PD by PATM plus OT by 21. So OT is the oxygen transfer rate, PD is the pressure at a particular depth, okay, from where the aerators are coming in, and then P atmosphere is the pressure of the atmosphere, and CSTH is uh, the saturation concentration. Okay, the concentration at the standard temperature and pressure. Okay, that is 9.6 given in the question. So if you put all these values, you will get the average concentration, and then AOT. AOT is the average oxygen transfer rate, that is equal to the standard oxygen transfer rate into some constants. So all these constants will be given. Okay, alpha, beta, F. So these are various constants that are applied to derive. It's a kind of empirical equation which you have to memorize. There is no other go. So I just wanted to tell you about this. There is not much significance for this question, but remember that whenever we put the aeration system in any place, so the transfer of oxygen rate depends on the temperature, on the pressure, on the saturation, oxygen concentration. Okay, so all these things affect the oxygen transfer rate. So that's how you have to solve this problem. Earlier, one more problem I showed you. So that was also the same similar kind of thing. So all these parameters will be given. You have to find out one of the missing one. Okay, so don't worry much about it. Simply you have to memorize the equation. Right? Okay. Next question. Which of the following factors affects the efficiency of coagulation-based sedimentation in wastewater treatment? So if sedimentation is happening after coagulation, which of these factors will affect it? D, all of the above, because pH definitely, every coagulant have a pH range in which they are mostly active. Okay, so pH is important. Temperature is also important because a low temperature can slow down the agglomeration of the particles. So that's why the coagulation will be affected. Then surface overflow rate. If you increase the surface overflow rate, then the coagulation will be decreasing. So like that, it will affect. During secondary treatment of wastewater, the influent from the primary clarifier enters the secondary treatment of wastewater, the influent of primary clarifier enters the aeration tank. That is very dirty.
Leaching tank.
Yeah, so aeration tank it enters. A probable electron acceptor in anaerobic anoxic respiration is, which of them is the probable electron acceptor in the anaerobic or anoxic? So all of them, because organic matter, nitrate, sulfate, everything is used as an electron acceptor in this kind of system, except for aerobic. In aerobic, we have oxygen as the electron acceptor. Okay, so advantages of biological treatment system over physicochemical system are cost effectiveness, lower energy requirements, both A and B, or less time consuming. So both A and B, because biological systems are cost effective, they will need very less or no energy, but they are very highly time consuming because it depends on the metabolism of the bacteria. Okay, so when organic matter is used as an energy source, it is converted into stable end products by the process of anabolism, catabolism, catalysis, pyrolysis. What is it called as? It is called as, it is not it is not catalysis, it is called catabolism. Catalysis is something where some catalysts are added to uh, for some reaction. Okay, so it is called as catabolism, where organic material is used as an energy source and converted into stable products. Endogenous, next question, endogenous respiration of a process, sorry, yeah, endogenous respiration of a process is a process of derivation. I think the answer is already shown here. Yeah, so endogenous respiration, which we discussed during the growth rate of the bacteria. So it basically deriving the energy through oxidation of the own protoplasm of microorganisms. So these microorganisms in the dead phase, they will feed onto themselves on the dead bacterial cells. So that's why the energy derived through the oxidation of the own protoplasm is known as the endogenous respiration. Oh, it's are you able to see the slides? Are they changing? I don't think so. It is changing, right? You can see question number 25.
Yes.
25, right?
Yeah.
Yeah. So it says that identify the most appropriate choice for statements A and B. The nutrient requirement is lower in anaerobic process than aerobic process. The growth rate of microorganism is lower in anaerobic process. So you have to find out the most appropriate option. Are both the statements false? Please look into it again. So actually, when we compare the anaerobic process and the aerobic process, the amount of biomass or microbes produced is much higher in aerobic process. Okay, because the energy generation is more, so much higher uh, growth will be there in aerobic. So if aerobic process is having more growth, then the nutrient requirement will be also higher, right? So that's why the nutrient requirement of anaerobic process is lower. Okay. And again, the growth rate is also lower in anaerobic. So both the statements are true. Okay. So here both the statements will be true. The sludge volume index of wastewater sludge refers to what? Duration of solid retention, total organic content, sludge volume produced during secondary treatment, or settling characteristic of sludge. What does the sludge volume index refer to? I think we solved one problem also. That time I told you what is the significance of the sludge volume index. So it generally helps in understanding the settling characteristics. Okay, it helps in understanding. So how much volume will be occupied per uh, gram of activated sludge. Okay, within 30 minutes. So that's how we do the sludge volume index. So that helps in indicating the settling characteristics. Okay. I think this question is not applicable. This also we have seen. Okay. The rate of microbial growth and metabolism depends on F by M ratio, solid retention time, sludge volume index, or none of the above. Growth of microbial and the metabolism. It depends on what? It depends on the sludge volume. It depends on the food to microorganism ratio. Because how much food you are providing with respect to the microorganisms, on that only the rate of microbial growth will be depending. Okay. Okay. Okay, this similar problem we have already done to find out the sludge volume. And simply we have to divide the volume with the weight. So this is very simple. So 27 by 3, it will be equal to 9. Okay. Okay, last set of question that we will do today. So we have again the equations are given. Sorry, the data is given. We know the volume, the Q is known, S is also given, X, everything is given. So this is the set of data that is given. So I will just quickly go through like how to solve this. So first will be the F by M ratio. What is the F by M ratio? So F by M ratio is nothing but Q into S naught into V into X divided by V into X. So that will give you the F by M ratio. Similarly, I told you volumetric organic load. So here the X will not be there. So QS by V. So QS by V will give you the volumetric organic loading rate. How much organics are coming into the system with respect to the time per volume. So volumetric loading rate. Then what is the residence time or mean cell residence time? Similarly, the same formula that we will use, okay, Vx by Qr into Xr plus Qe into Xc. Okay, all these questions are formula based. So in this chapter, though conceptually you know how to do the mass balance and everything, but most of the problems will be formula based. So just make a note of all these formula, revise it again and again, and then you can solve. Last one, what will be the effluent BOD? So effluent BOD will be same as that of the aeration tank. As I told you, since it is same, it is a CSTR. So whatever was there in the tank, the same will be coming out. So effluent BOD will be same as the aeration tank, that is 30 milligram per liter. Okay, so yeah, so I think that's it from my side today. We have solved enough problems. We have seen how to what is the concept behind the ASP, how to do the mass balance, what are the important equations, and how the questions are asked. With that, we have solved many theoretical problems also, some settling problems, SVI problems, everything. So I hope the questions more or less in the exams will be like this. Okay, so I hope this will clear all your doubts. And if you have any more issues or anything, you can reach out to me at saha19akash@gmail.com, And again, we will have the next class on 24th February. Okay, that is Tuesday, 7 to 9 p.m. So see you in the next class. If you don't have any more queries, you can leave the session now. Thank you so much. Any doubts or any queries? Anything?
Sir, were you able to ask if the if candidates abroad can apply for the
Yeah,
exam?
actually, I didn't get a concrete answer, like any fixed answer, because no one was knowing much about it. Because that other thing, still people are not sure. I don't think
Okay.
abroad it is available. I have put a mail
Okay.
actually. I'm still waiting for their reply. So once I get the
Yeah.
answer, I will let you know. Because
Yeah.
I think my friends were also not clear. So I have asked the organization. They have not
Okay.
yet replied to me. So once I get it, I will
Okay.
let you know.
Yeah. This
Okay.
time I think registration is already over, so I have to apply only next time. But this information you're giving me is uh, is good for me for the next semester also. So
Okay, and
if you can let me know, it's good.
yeah, if I get the
Thank you,
reply,
sir.
because I don't have any personal like phone contact, I am also mailing them. So let me see when they reply.
Sure.
I will let you know.
Thank you, sir.
Yeah.